This is part 5 in a series on the origin of the elements. In this segment, we're going to talk about nuclear fusion inside high-mass stars. In a previous discussion, in a previous segment, we talked about what happens in low-mass stars. Actually, this also happens in high-mass stars. That is that we start with a star that's made entirely, almost entirely of hydrogen, but the hydrogen fuel gets used up and you're left behind with some helium ash. At that time, there's going to be hydrogen burning in a shell around this core, and this core is collapsing because it's no longer making energy, and so the pressure isn't able to counteract gravity. Outside of that, you have the rest of the star that's really not doing much. Later, after the helium that was here has managed to switch on fusion and start to produce carbon, it will all get used up. So we end up with a system where there's carbon ash in the center. The carbon is not doing anything. It has a shell of helium around it that's being burned. That's the helium that was being made here. Around that, it's got a shell of hydrogen that's being burned. And around that is the rest of the star that's not doing much. For low mass stars, this is where we get to. You don't get beyond sticking heliums together to make carbon in the core of the star. But for high mass stars, you can keep going. It's a temperature dependent thing. And basically in a high mass star, you're able to overcome the forces that stop it from collapsing. And so the carbon in the carbon atoms in the middle of the star continue to collapse until it gets hot enough to stick carbon atoms together. Eventually you run out of carbon, and then you start to make oxygen stick together. After that, you stick neons and so on. And so what you end up with is something that looks like this. So here we have what happens after you've been through all the different types of fusion that you can do. So you started out with hydrogen fusion, then you had helium fusion, then carbon, then oxygen, then neon, then magnesium, silicon, and what's left behind here is iron. The problem is that once you get to iron, you can no longer fuse elements to make energy. And so at this point, the star is going to die pretty rapidly. Now, this is what we expect for stars greater than probably about 10 solar masses. And for those temperatures, you're able to go through all these different types of fusion along the way. There are a few that may stall out, so you may get to fusing carbon, but get stuck with something that's made of oxygen, neon, and magnesium, and not get past that. And that's maybe in the sort of 8 to 12 solar mass range, but certainly beyond about 12 solar masses, you should be able to do all of these different types of fusion. So the star has made all of these different things inside. So let's talk about those different cycles of fusion. We talked about hydrogen and helium fusion or burning in a previous segment because that happens in the low mass stars. And you have to go to the high mass stars before you get carbon fusion going on. And so here you can see a schematic of the different things that you can form. So there are different things that can happen when you stick two carbons together. If they just come together and don't throw anything out, you get a magnesium 24 isotope. But you might throw out a neutron, and that would give you a different isotope of magnesium. Or you might throw out a proton, and then you get sodium. Or you might throw out a helium or alpha particle, and that would give you a neon. And you might throw out two helium particles, and that will give you an oxygen. And so these are all different things that you can make. The most important, the one that seems to happen the most, depend in the sort of conditions that are expected to be there inside the star, are the ones that stick two carbons together to make a neon and ejects an alpha or helium particle. And you can see that represented here. I've got a carbon 12 here. That's 6 neutrons, 6 protons, another carbon 12. And when you bring them together, you get a neon, which has 10 neutrons and 10 protons, and a helium. Okay, so now we've made a bunch of neon. Now we're going to stick neons together. And so there are lots of different things that we can make. But basically, as we're sticking neons together, we're going to make magnesium. This happens as you have the core collapse and heat up. Again, this happens after each subsequent set of fuel is used up. So after the hydrogen is used up, the core collapses and heats up, gets hot enough, and helium can fuse. And then that gets used up, and it collapses and heats up, and then carbon can fuse. And then this time it is neon that can fuse. From the neon, we're going to get lots of magnesium. Now, to get neon to burn, you need very high temperatures, higher than we needed for helium or for carbon. And then the next step would be oxygen burning. So here you can see various different possibilities. Again, if you just stick two oxygens together, you're going to make a sulfur and have some energy released. But you could also make a phosphorus or a silicon with a helium, or a magnesium with two heliums, or a different isotope of sulfur with a neutron. And so that's represented here. Now, in this case, the most likely one to happen in the sort of conditions that we see inside the stars are going to be the ones that give us silicon. So here I've got two oxygens that we stick together, and then we get a silicon and an alpha particle or helium nucleus. Now, we're going to get magnesium at some point as well along the way. And so if we find magnesium on here, here's magnesium, the 12th element. And you think that we'd stick two of those together and get chromium. And that's certainly a possibility. But the most likely things to form are the things that are the next elements along the table. So it's actually going to make lots of aluminium or aluminum, silicon, phosphorus, and sulfur. And you can see here how complicated this can get. So here I've got a magnesium, and from this magnesium, I could make aluminium. I could make a different type of magnesium. Once I've got my, and I could make silicon. So there's all sorts of different places that this could go. Once I've got silicon, then I can start to stick silicons together. Now, at this point, you need really high temperatures. This is, 2.7 billion Kelvin that's needed, and incredibly high densities in order to stick silicons together. And the first thing that's going to happen is you're going to stick two of these silicon 28s. That's the most common isotope. You're going to have two silicons stuck together, and you'll end up with these two coming together and giving you a nickel 56. So all of the protons and neutrons have gone into here to give us nickel 56, and that releases some energy. But then we get a couple of subsequent reactions. So the nickel is going to absorb an electron. So what it's doing is it's capturing this electron, and the electron merges with a proton to make a neutron. So one of the protons in here gets converted to a neutron. So we go down an atomic number, and so we get cobalt. If we remove an electron, that it gets absorbed, we produce a neutrino. Well, that's what this little new particle is. The same thing happens again. I've got a cobalt here. It's still the same mass, but now it has less protons and more neutrons than the nickel did. And we're going to have it happen again. We're going to have one of these protons combined with an electron, and it's going to give us another neutron, and we're going to lose the neutrino. And so this is what we end up with as a result of this silicon fusion. We're sticking two silicons together, and we make something that's unstable, and we end up with iron 56. Now, silicon burning is extremely short-lived. You've got to remember that with each stage that the star is using its fuel, you take hydrogens and you use 4 hydrogens to make a helium, and then you use 3 heliums to make a carbon, and then you use a couple of carbons to make an oxygen, and then you use a couple of oxygens to make the next thing, and so on. By the time you get to silicon, there's a lot less actual elements left, individual particles, individual nuclei left to stick together. And you have to use them up really fast to maintain the pressure-gravity balance in the star. So the star is balancing gravity trying to pull all the atoms in and pressure pushing it out. And as soon as it runs out of fuel, that balance is broken. In order to keep that balance during the fusion times, the fusion has to be producing a lot of energy. It really doesn't take very long for the silicon to go through this process. So remember, we're taking 2 silicons to make a nickel, and then that does an electron capture, and we get iron 56. On average, a star is going to use up its silicon in 1 day. So once you've got to the point of having a core full of silicon, it's not going to last very long at all. Now, we can't see inside the star, so we don't know exactly when that's going to happen for a given star. And now we've got iron 56. So that's the thing that gets made. And this is the most stable isotope in the universe. We talked about this in a previous segment where we talked about how there's a binding energy associated with each element. The one that has the most binding energy per nucleon, so that means the protons and neutrons, is iron 56. That means that you cannot make it more stable by adding more stuff to it. You can't fuse it to itself or anything else and make it more stable. And that means that you're going to have to give it energy. So you can add things, you can fuse it, but it won't produce energy, it will use up energy. So when we talk about what's happening inside a star over the course of its life, it spends most of its life doing hydrogen burning, either through the proton-proton chains or the CNO cycle. We talked about those in a previous segment. And those have modest temperatures in the few million Kelvin range, and they produce helium, and they produce quite a lot of energy per nucleon. So there's quite a lot that comes out from doing this. Then we've got heliums that we stick together. It's called the triple alpha because a helium nucleus is the same as a radioactive alpha particle. That takes about 100 million Kelvin, and that produces carbon and oxygen, but it also produces a lot less energy per nucleon. So it's a lot less efficient than that first hydrogen burning. And then we've got carbon. We're sticking carbons together, and that takes even higher temperatures, and that's going to make a bunch of oxygen, neon, sodium, magnesium, and again, produces even less energy per nucleon. And then we've got oxygens that we're sticking together, and that's taking 1 billion Kelvin and is making magnesium, sulfur, phosphorus, and silicon, and really doesn't make that much energy in the process. And then we've got silicon, and that takes 3 billion Kelvin to stick it together, and then it makes cobalt, iron, and nickel, but it doesn't produce much energy, and that's why it gets used up so fast. Going on inside one of these big massive stars, the core is actually a tiny bit in the middle. Most of the star is just hydrogen and not doing anything. This is showing you a schematic of, this is the tiny core in the middle, and inside of that, you've got all of these different fusion shells going on, and in the middle, you've got the iron, and it's not doing anything much. And this is kind of giving you a crosscut through that so you can see, and how long it takes for each of the core burning stages. So for a star like this, it'll last 7 million years for its hydrogen fuel to run out, but then only 500,000 years for its helium, and then only 600 years for carbon, only a year for neon, only 6 months for oxygen. And again, once you get to silicon, it's all but done for. The silicon is making iron. And once you've got most of this, the core being iron, things are going to start to go wrong. So let's talk about what's happening there. So here's my star. It's got all of these different fusion shells. Remember, this is not to scale. The rest of the star is much, much bigger. But you've got all of these different fusion reactions going on, but the core is made of iron and it's not doing much. As I said, you cannot fuse iron and get energy out of it. You can't produce energy in any way from iron. You can stick them together, but you're going to use up energy. It's going to collapse under gravity. Remember that once it stops making energy, it's going to cool down, and that means that the pressure drops, and that means gravity is going to win, and so it starts to collapse under gravity. But if it collapses under gravity, it heats up. This is the same cycle that we've been through every time, but this time it's never going to be hot enough to create fusion that gives us energy. And so the temperature is getting hotter and hotter, and at some point, the temperature in the core is comparable to the temperature needed to break apart an ion. So we call this photodisintegration, or the gamma process. The photons, the light that's in here at this temperature, is gamma rays. And those gamma rays are high enough energy that they can undo what was done in putting things together. So it's breaking the binding energy. The iron is broken apart. So instead of staying as iron 56, it's broken apart into its constituent pieces, which is essentially 13 heliums and some neutrons left over. It takes millions of years to get from just having hydrogen and going through all the different fusion cycles to getting just iron in the core, and then within a fraction of a second, all of that iron is then photodisintegrated back into heliums. And so consequently, although it makes iron in the core, that iron that's in the core is destroyed and it's not ejected out into space. We'll talk a bit more about where iron comes from later. But the disintegration is going to continue. We've got these helium nuclei, and there's still lots of energy, lots of photons around. And so those heliums can fall apart into their constituent parts. So our helium-4 is going to fall apart into 2 neutrons, 2 protons, and then there'll be 2 electrons. But the electrons and the protons can come together And that's shown here. So we've got a proton and electron, and that will make a neutron and a neutrino. And so what we've got is that the proton and the electron get squished together so hard that it makes neutrons. And so now everything is made of neutrons, but there's still no way to make any energy. And so the thing continues to collapse. So we've got this core that is very, very small. It's very, very dense. And the neutrons are falling in and getting hotter and hotter. The core is going to keep collapsing until something stops it. Now, for the lower mass stars, that's actually a quantum mechanical effect called neutron degeneracy. But what's happening in the meantime is you've got stuff that was around the core falling in and getting hotter and hotter. And that, as it heats up, the gas gets higher pressure. Temperature and pressure are highly correlated, so the pressure goes up, and that can push back against gravity. And because it's collapsing rapidly and heating up rapidly, that's a rapid push out of pressure, and that generates a shock wave that goes through the rest of the star. And so what we get is the tiny bit of core right in the middle, and it's even smaller than this because it's the iron core that's already collapsed down. It's going to drag some of this other stuff with it and some of this stuff around it. And then that's going to get pushed back out because of the high temperatures generating high pressures. And so what we get is a shock wave that's propagated through. And so this is showing a model of how that would look. So now all of these different layers are going to get mixed into each other. And so you're going to get fusion going on in the explosion, in the process of that shockwave pushing material out. During the explosion of the star, you will make new elements, including nickel and iron and cobalt, that will be part of what fuels the supernova, the brightening of the star as it's exploding. So here we can see one of the most famous supernovae. This is the supernova remnant, the Crab Nebula. This was actually observed in China in 1054 AD. And what we can see here, this is all material that was once part of the star, and it's had about 1,000 years to spread out in all directions. During the course of the explosion, you're making so many new elements that are radioactive that there's a lot of energy. It's like a really big nuclear explosion. And so we go from having something where you really don't notice that there's a star to having a really, really bright star appearing. And so what we get is that in distant galaxies, we can see a supernova that's almost as bright as the entire galaxy all put together. So if you add up all of the stars here, it's almost as bright. The supernova is almost as bright as all these stars put together. And as I said, what's happening as this material is pushing out is that these massive stars, they will eject iron out into space because iron is being made during the explosion. It's not the iron that was made in the core of the star, but some will be made in the explosion. But that's not where most of it gets made. And that's a topic for a future video.